So, in yesterday's lecture, we saw the Einstein model. We call it Einstein solid because he assumed that each atom is a harmonic oscillator which is decoupled from rest of the atoms in the lattice, and so all the atoms, they vibrate with the same frequency, and we derived an expression for the specific heat of an Einstein solid. We call it Einstein solid. I mean, a solid where the atoms are decoupled from one another and each atom is vibrating about its lattice point and can be treated as a three-dimensional harmonic oscillator. So we derived the expression for specific heat, and we showed that at high temperatures it does tend to a constant value, which is 3R, and at low temperatures it drops very sharply, exponentially. In fact, the specific heat becomes exponentially small, right? And I hope that you understand the physical meaning of this, why the specific heat becomes exponentially small. The reason is that the energy which is accessible to the oscillators, the thermal energy, right? This energy is much less than the energy gap between the ground state and the first excited state. So therefore, the probability of finding an oscillator in the first excited state is very small. Most of the oscillators, the atoms, most atoms are oscillators. So most of these atoms are exploring the ground state, right? And therefore, the ground state is the half h bar omega E. That's the energy in the ground state, which is independent of temperature, and if you take the temperature derivative, it goes to 0, right? So that is why the specific heat of an Einstein solid is very small at low temperatures, at temperatures that are much lower than h bar omega E, where omega is the frequency of these oscillators, the atoms, and it's also called Einstein frequency, right? Now today we are going to look at another model, which is the Debye model. The problem of specific heat. So let me call it heat capacity, because as you have seen, I fix the number of atoms right at the end, right? We take some number of oscillators in a system, and unless it is Avogadro's number, you don't get the molar specific heat, right? You know that. So okay, so this is the heat capacity, and the expression for this is rather simple. You know, lattice heat capacity. So associated with the lattice vibrations, but we don't have to be so explicit. You know it by now. So the energy of lattice vibrations, is given by summation over all the modes. So all modes, or all phonons in the current parlance, you will say all phonons, or you will just put a shorthand notation n comma s, k comma s, and then n k s plus 1/2 h bar omega k s, and the heat capacity C is nothing but the temperature derivative of U. That is it. So the problem is as simple as this, and this term disappears. So basically what you remains with is just this del T of summation Ks, and then just the product of these three. H bar can also come out, but I'll just keep it here. So you have H bar omega Ks nks. That's it. Now the difficulty is that we don't know the analytical form of omega, except in very special cases, like for instance in the case of 1D chain, we do know that the expression for omega. But if I make the problem a bit more complicated, you will already start running into trouble, into problems. So for instance, from monoatomic, when I went to diatomic, you had two branches, and the expression was already looking very complex. I mean, it had, two terms at least. And then if I go to even more difficult case, it will become even more serious. And that is not the only issue. The other issue is that if you go to 2D or 3D, then in that case, suppose let's take the case of 2D. So in 2D, you know that the primitive cell in the reciprocal space or the Pilwan zone, it goes from minus pi by a to plus pi by a in both the directions, up and down, and the center is gamma. Okay. So now the dispersion, which is omega versus k, would depend on the direction along which you are traveling, right? If you're traveling along the x-axis or the kx axis, let's call it kx. So if you're traveling along this axis, omega may have some form, some analytical form, even if you can find that form. The analytical form along this direction may be different, okay? The analytical expression along any arbitrary direction could also be different, okay? So omega can be different along different directions, plus the limit of integration. So you will integrate from the zone center to the zone boundaries, because you want to take all the modes in the first Brillouin zone, and the limit of integration will also depend on where you are, in which direction you want to travel, right? And then of course you have to sum over Avogadro's number of modes. So that is again a complex problem. You can turn it into an integration, that's another thing. So let's see what Debye did, how he negotiated this. So to understand that, I'll take a simpler case. I'll take a case of diatomic chain. So let's say you have to find the specific heat of diatomic chain. I'm taking this example because you can numerically find the specific heat of diatomic chain pretty nicely. You have to integrate numerically, and then you can also calculate the specific heat using the Debye model, and then you can compare the two and see how well they compare with each other. Okay, so that's why it's a very nice example. So you know that in diatomic chain, we don't have to worry about too many directions, because there is only one direction in 1D world. That's nice thing. That's why I took the diatomic case. Here is the dispersion omega versus k. So you are at, this is the zone boundary, the boundary of the first Brillouin zone. And how many modes, how many branches do you have here? Because we are dealing with diatomic chain, you have two branches, the acoustic and the optical branch, right? By now, these things should be kind of very nicely known to you. So this is how it looks like, okay? And of course, it's there on this side as well, but I'm not drawing it because I'm a bit lazy and I'm not too good at drawing things. So this is the direction of the chain, and you know this point is how much? What? Pi by a, right? Now suppose we have to find the heat capacity of a diatomic chain. You will start with this expression. The first thing that will happen is that the S will drop out, or no, S will be there, because you have to count over two modes. For each value of k, there are two values of S, right? So if you take this expression, so you will write C is equal to, H bar is going to pop out, right? So you will have H bar del T, and then you have summation over k. And what else? What is there inside? Inside you have two terms now. One is omega k and k 1 plus omega k and k 2. Now here omega 1 refers to, let's say, the acoustic branch, and omega 2 refers to the optic branch, right? Taking advantage of the fact that the k points are very closely spaced, and the amount of space that each k point takes is 2 pi by Na. So therefore the density of k points will be Na by 2 pi, right? So we can convert this summation into integration, and the recipe is still the same which we derived in a previous class. If you are summing over k a function fk, right, and because the k space is quasi continuous, and if the function is slowly varying, by slowly varying I mean if you choose an infinitesimal volume, then the function should not change, it should not have a discontinuity, it should not become very large suddenly as you go a little bit away, slowly varying, then you can transform this into an integral, and that integral would look like this. So here you are summing over all k's in the Brillouin zone, you will integrate over the Brillouin zone, and then you have f of k, then density of k points, rho of k, and then the volume of elemental volume in the k space, right? Now in the case of 1D, how will this transform? What will rho k be? I just answered that question. In 1D, rho k is Na by 2 pi, right? What about d tau k? D tau k is nothing but dk, isn't it? So therefore, this expression would be nothing but the integration over the Brillouin zone, which extends from minus pi by a to plus pi by a, and then the function f of k, and then the density, which is a n over 2 pi dk, right? So you can plug that in over there. So what you're going to get is, you can simplify it. So you get h bar a n over 2 pi, right? And then you have del t of this integral, okay, and this integral is over these two terms. So omega k1 and k1 plus omega k2 and k2 dk. Now if you, I mean, at least at this level of your studies, since you are probably doing a course in computational physics, I don't know if you're doing it already or you will do it in future. This is something, because you know the expression for both the branches, omega k1 and omega k2. So in principle, you are in a position to solve this integration numerically and get the answer, right? But still, it's a difficult task, because you know the expression for omega is, as I said before, it has at least two terms in there, the k1, k plus k prime by m, and then plus under root of something. So let's see what Debye did, how we can solve this problem using the Debye model. Okay. So what did Debye do? So Debye, he said, or rather, I mean, I would say, if we were to use Debye model to solve this problem, what we would do is the following. So Debye said that we assume we assume that there is only one branch, and that branch is given by omega equals Vk, where V is a constant okay. So, if V is a constant, then this is a linear dispersion. It is a linear dispersion. So, he said that you have, in reality you have two branches, but let us work with only one branch, and let us assume that for that branch omega is simply given by Vk. Now, you would be quite, I mean you would say, are you kidding? How is this going to solve this problem? Because the actual form of omega versus k is definitely non-linear, right? And it is, of course, maybe if you draw a straight line, it might go close to this branch, but it's still too far from this branch. I mean, how are we going to approximate the optical branch with this expression, right? That is the thing. But Debye model does not stop here. That is the first point of Debye model, that you replace both the branches by this. The second point in Debye's model is that till how far should you take this branch? You know, you can just go on and on and on and on and keep drawing it, right? Okay, you consider only up to the first Brillouin zone, but you know that k extends all the way up to infinity, right? So, where shall we stop it, right? So, the Debye said, look, omega is equal to Vk, that is good, but only when k is less than or equal to some cutoff, which is the Debye wave number. He said, look, omega will be Vk only when k is less than or equal to Kd. It will be 0 otherwise. The moment you go outside this, it is going to disappear. Now, where is Kd? So, Kd is somewhere on this x-axis, somewhere. It could be here, it could be here, it could be there. And Debye does not stop here. He gave one more condition for you to find out what Kd is. So, how did he derive the value of Kd? Or in modern language, what should we do to get the value of Kd? So, this is the most important point actually. So, now actually I should make it mod of k. So, now this is like a Debye zone, just as this is the Brillouin zone, which extends from minus pi by a to plus pi by a. There will be a Debye zone which extends from minus Kd to plus Kd, right. So, maybe your minus Kd is here and plus Kd is here. So, this is the zone that extends from minus Kd to plus Kd. Within that zone, you will just take two straight lines and solve the problem. So, how to find Kd? So, he said that the number of modes in the Debye zone should be equal to the number of modes in the Brillouin zone of the original problem, right. So, let me make the statement. So, Debye said that the number of modes, I mean you have to choose Kd in such a way that the number of modes in the Debye zone, well actually I tell you the truth, it is called Debye sphere, because in 3D this zone will become a sphere. You can already start envisaging it, that in 3D it will become a Debye sphere, in 2D it will become a Debye circle. So, we call it Debye sphere, quote unquote, just as we call it a Brillouin zone, irrespective of whether it goes from minus pi by a to plus pi by a, or it is in 2D or it is in 3D. In 3D it is a cube, in 2D it is a square, right. So, we call it Debye zone, or better, Debye zone is my own invention. So, let us not go by that, because you will get confused, you will not find it anywhere in the textbooks. So, let us call it by the name which everyone's call it, and I am putting it quote under quote because it is not a sphere right now, it is just a line segment, right, but it is a Debye zone. So, he said that the number of modes in the Debye sphere should be equal to the number of modes in the original problem. So, this should be equal to the number of modes in the original problem. Okay. Let us use this recipe for this particular problem, right. So, you know the right hand side of this equation, because now I want to find Kd, where everything else otherwise is pretty straightforward, right. Omega is given by Vk, I need to find Kd. So, to find Kd I need to know this and I need to know this. So, what is this? How many modes are there in the original problem? Sorry? That means you have not understood anything so far. So, these lectures are completely useless for you guys. We have, you know, this 2D, this diatomic chain, number of lattice points are always n, right. But at each lattice point there are 2 atoms, right. So, there are 2 n normal modes. For each k value there are 2 omega values, and how many k values are there in the first build one zone? N, right. Unless you go and revise these things, I do not think some magic is going to happen, right. So, a given n, a given k, for every given k you have 2 values of omega, and how many k values are there between minus pi by n plus pi by a? Capital N. How do you get that? Using the periodic boundary condition, right. So, please do not do this mistake, otherwise nothing will remain. We are not doing any maths, sophisticated maths here, it is just logic, right. Periodic boundary condition use, and in 3D it is 3pn modes if you have p atoms per unit cell. Okay, so here on the right hand side we know it is 2n. On the left hand side, who will tell me what is there on the left hand side? So, fine, right hand side is 2n, left hand side, well, left hand side is the size of the Debye zone multiplied by the density of k points, isn't it so? How, I am asking you, how many k points exist inside the Debye zone or inside the Debye sphere? So, what will be your answer? You know that all along this x axis, this k axis, no matter where you are, k points are equally spaced, and the spacing between any 2 successive k points is 2 pi by a n, right. So, this spacing is not changing independent of where you are. So, that is why the density is the same. So, this is 2 pi, this is 2 pi by a n. That is why the density was a n by 2 pi, no? Right, and this is the same everywhere, no matter where you go. So, your Debye sphere extends from here, this is minus Kd and this is plus Kd, let us say. So, what is the size of the Debye sphere? Minus Kd to plus Kd, that is twice Kd, multiplied by the density of k points. Density of k points is how much? Yeah, a n by 2 pi. Okay. So, now what happens? 2 cancels, and n cancels, what remained? What you get is Kd is equal to 2 pi by A. And this is very nice. This is very nice because this is the 2 pi by A is what? 2 pi by A is sitting here. Right? Now, I showed you the other day that you can take this branch over here. This is the second Brillouin zone, right? You can transport it from here to here by adding 2 pi by A. You can take this into the second Brillouin zone by adding minus 2 pi by A. You remember I called this as 1 plus meaning the positive half of first Brillouin zone. This is 1 minus the negative half of first Brillouin zone. Then this is 2 plus the positive half of second Brillouin zone. Then this is 2 minus the negative half of second Brillouin zone. So what is in the negative half of first Brillouin zone can be mapped onto the positive half of the second Brillouin zone by a reciprocal lattice vector 2 pi by A, isn't it? So I can take this branch over here. So this branch can come like this. And similarly on this side, I can extend it to second. And once I have transported the branch, then I am now working in the extended zone scheme. I told you that, it is a convention to work in the reduced zone scheme, which means to fold all the branches within the first Brillouin zone. But it's not uncommon to see, to spread them out and go into the other zones, right? So you don't need it now here because you have copied it into the second zone. And now where is the Debye? Where is Debye term? Debye mode? So now let's draw. So this probably is, so you know that the Debye omega equals Vk is extending from minus Kd to plus Kd, or this is, so basically it will look something like this. So you have, what have you done? Try to see. You have replaced this branch and this branch by a yellow branch. The nice thing about the yellow one is that it is a linear, a straight line, which has a cutoff, and the cutoff is Kd. Why does it work? It works, of course, approximately, but why does it work? It works because at places you are underestimating the actual dispersion, but then there are also places where you are overestimating the actual dispersion, so it gets averaged out. So when you work out the energy using this expression or the specific heat, when you sum over everything, so at some places you have underestimated the actual dispersion, at some places you have overestimated the actual dispersion. On an average, to first order, you get a very good estimate of the specific heat of a real solid by replacing something which is very complex, whose analytical form also you may not know, by something which is, it cannot be any simpler than this. It's just a straight line, right? So this is Debye model. That is it. That is it. So what do you have to do now? You will replace omega by Vk, and integrate it from 0 to Kd. Done. You may have to still use numerical integration because in Nk you have the temperature dependence. So you have to take the derivative of that. So this is a solvable problem. So for Nk you will write now 1 over exponential beta h bar Vk minus 1, okay. Take the temperature derivative, then integrate it and so on and so forth, and you will get the answer. Now let's try to extend this to 3D. So let's go to, or shall we first go to 2D? Let's go to 2D, or let's go directly to 3D because we don't have much time. So in 3D, this is how the build one zone is going to look like. We are assuming a cubic lattice. Wow, doesn't look very good, but it's okay. And let's assume 3D monoatomic lattice. What does monoatomic means? At each lattice point, there's only one atom, one oscillator at each lattice point, or you can say one atom per unit primitive cell. Okay, so 3D monoatomic case. You know how the actual dispersion looks like? Yeah, let's try to draw it. For 3D monoatomic case. So now, of course, it will depend on the direction as well. The dispersion will depend on where you are traveling. So this is the center of the Brillouin zone, and this point is the gamma point. So you can go from gamma point to the phase center, which is the M point, or you can go from M point, gamma point to the X point, which is the corner here, or you can go pick some arbitrary direction, right? So you can go along the body diagonal of the primitive unit cell, you can go along the face diagonal of the unit cell, or you can go along some arbitrary direction. Now, if you choose to go in this direction, you will reach the Brillouin zone shortest, and that distance is just pi by a, right? Because it extends from pi by a to minus pi by a in all three directions, right? And if you choose to go from gamma point to X point, that will be the longest distance to reach the zone boundary, right? And in between, you have all possibilities depending on what direction you take, isn't it so? So, for instance, you can decide to go from here to, let's say, this point on this face on the, so that way also you will reach the zone boundary, but the distance that you have traveled now is something in between this distance and this distance, right? So that means now I cannot just draw one dispersion like this and then wash my hands off and say, okay, it's done. No, that's why the problem is complicated, and that's why we should appreciate Debye. So let's draw it. So let's say going along the x-axis, so this will be kx. So you know you are going to reach here. This is the end boundary of the zone, right? Suppose you are traveling along the face, the body diagonal. If you are traveling along the body diagonal, then you know that you have to travel an extra distance to reach the body diagonal. Then your zone boundary is here. If you are traveling along some other arbitrary direction, then the zone boundary will be somewhere in between these two extremes, right? So it can be here, and so on and so forth. Same about the dispersion. So here, do you have any optical branches? No, we are dealing with monoatomic chain. But do we have one acoustic branch or two acoustic branches or three? Three. And these three are one longitudinal and two transverse, right? So you have, now it is possible that you may see all three of them, which means they are not non-degenerate, or it is also possible that you are going in some low symmetry direction and they are degenerate. So let me draw along this. Maybe they are like this, maybe very close by, but they are resolvable. Okay, maybe in this direction they are like this. And maybe in this direction, which is some low symmetry direction, maybe two of them at least, the two transverse ones are maybe not resolvable, and they're just superimposed over each other, and this is the third one. And you can have one more, and you can go on drawing these diagrams. There are so many directions that you can work with. Of course, Thankfully, it's a cubic symmetry. So therefore, working in with only one octant is enough. Everything else is then just the isn't it, because of the cubic. But even then, it's a lot. So now let's use the Debye's recipe. So how would you solve this problem using Debye model? Point number 1, Debye's point number 1. So Debye said that we will assume omega to be just a linear dispersion Vk. But now that you are working in 3D, pay attention. Now that you are working in 3D, and Debye was completely aware of this fact that in a 3-dimensional solids, and in fact let me say something before I complete my previous sentence. Debye was completely aware that in the solid, the sound propagates as waves, as vibrations, right? This is how it propagates. So by taking this linear, when omega is linear, for instance, on an elastic medium, on a string, when you excite waves, for those waves, the dispersion is linear, right? So that is what Debye thought. He thought that the matter is just a continuum, okay? And the waves travel as the waves would travel on a string, and therefore he said omega is equal to Vk. But he was also aware that he has to put a cutoff, and that cutoff will come from the theory of normal modes, which was known from the previous century, which was solved by Bernoulli's brothers or a family. I mean, 7 Bernoullis, all geniuses. Some of them worked on the problem of normal modes and solved it. Solved it long time back for people to make use of it. So he said, yes, omega is Vk, perfect. But remember, now just as here in actual dispersion there are 3 branches, we also have 3 branches. We also have 3 polarizations: longitudinal, transverse, transverse, right? So that much he was aware of. So he said 3 kinds of waves can propagate. So therefore omega equal to Vk. But remember, how many branches are there? Number of branches 3. Now you can assume that all 3 are degenerate. So for all 3 of them, it will be Vk. Otherwise, it will be V1k, V2k, V3k. If you want to make your life complex, you can do that. But there is no reason for us to do that. We can just take the 3 branches to be degenerate. So we are assuming the 3 branches to be degenerate. Degenerate 3 branches. That won't change anything. Point number 2, we have to set a cutoff. And how should we set a cutoff? We will set the cutoff using the same principle. The number of modes in the Debye sphere. Now we are really in a 3-dimensional space. The reciprocal space is also a 3-dimensional space, and there you would draw a sphere whose radius is kd. So its volume will be 4 by 3 pi kd cube, right? So that's the volume of the Debye sphere, 4 by 3 pi kd cube. Now we have to multiply this number with the density of k points in the reciprocal space. So that density, in the reciprocal space will be cube of that density, whatever that was, and that we have derived in the previous class, and that is nothing but the volume of the sample divided by 8 pi cube, right? So it will be a cube n cube. And so this will give you what? This product will give you what? Number of k points in the Debye zone or in the Debye sphere. Now if I have to multiply it with 3 also, because Debye also assumed 3 branches. Each branch has to be taken into account. So this is the left hand side now. These are the number of modes inside the Debye sphere. And this should be equal to the actual number of modes in our problem, and that is 3n, because we are dealing with monoatomic lattice. So that is 3n, right? So now you can simplify it. 3 and 3 will cancel out, and some other stuff will happen. and n will remain, and v by n will become little n, that is the number density. So, if you solve it, you will see that the radius of the Debye sphere will come out to be 6 pi square, 3 will cancel out, and then we will be remained with 4, and this 4 and 8 will cancel out. So, 2 into 3 will be 6, so 6 here, and you will be left with pi square, because pi and pi cube. So, 6 and then n to the power 1 by 3. This is the radius of the Debye sphere. Okay. So, what have we done? Suppose, because I cannot draw a sphere on the board, I will draw a circle. So, this is my Debye circle. Let us say if you are dealing with 2D lattice, and the first Brillouin zone of the actual lattice may look something like this. And the number of, sorry, ये क्या कर दिया? And the number of modes within this yellow square is equal to the number of modes within this white circle. And what is the white circle? The white circle is the Debye sphere. And what is the yellow square? The yellow square is the actual Brillouin zone, the boundaries of the actual Brillouin zone. The boundaries of the actual Brillouin zone. That is the comparison between the Debye and the actual. What is same about the two? The number of modes in the Debye sphere is equal to the number of modes in the actual Brillouin zone, and that limits the size of the Debye sphere. Otherwise, the Debye sphere will go on extending. So, you have to impose a condition, and the condition is that you have to have the same number of modes as they are in the actual Brillouin zone. And why does it work? It works because the law of averages favors Debye theory, because at some places the dispersion is overestimated, and at some places the dispersion is underestimated by omega equals Vk, right? And how do you take care of complex solids where you have optical branches also? Because you just need to extend the Kd. Kd will go on extending. So, let us take one more example to make this very, very clear. So, my next example is 3D diatomic. Now, if you have really understood the concept, you will be able to tell me what should be the radius of the Debye sphere for this problem. Now, in this problem, because it is a diatomic lattice, number of atoms per unit primitive cell is 2, or 2 atoms per basis point. So, the number of modes will be 3pn. So, p here is 2, so 6, right? And where are the other 3? Those are the optical branches sitting over there, right? So, let us use the same recipe. So, if you use the same recipe, what will be on the left hand side? Left hand side will still be the same, 4 by 3 pi Kd cube. That is the volume of the sphere, Debye sphere, multiplied with the density of points, that will be V over 8 pi cube, and then multiply it with 3. Why? Because Debye said take 3 branches, right? And this should be equal to what? The total number of modes, 6n. So, in this case, what will be the radius of the Debye sphere? So, Kd will be 12 pi square n to the power 1 by 3. Are you surprised? The radius of the Debye sphere has increased. Why has it increased? Because you have to accommodate more modes. Earlier, you had 3n modes. So, the radius of the Debye sphere was this much. Now you have 6 n modes, so the radius of the Debye sphere has become this much, right. So, basically what you are doing is you are extending this linear dispersion to a larger distances. Why? Because you have more modes and you will unfold them to the second and the third and the fourth Piltwan zone, and they will go hugging the actual dispersion, somewhere overestimating it, somewhere underestimating it, and therefore the Debye theory will give you an approximate answer which is very close to the real answer, the real specific heat. All right. Now, once you know Kd, you can do everything actually. Now, the problem is solved. It's just a matter of doing a little bit of maths. But let me just define a few things. So, since you know Kd, if you multiply this Kd with a temperature which is often written as theta for some strange reason, not as T. I would love to write it as T, but or I should say I am tempted to write it as T, but let me just write it as theta. So, don't get confused, this theta is a temperature. So, Kd times, wait, I am making a mistake under all likelihood. Yes, I do. This is not Kd, this is Kb, Boltzmann constant, times theta d, where theta d is some temperature. This is a temperature. So, you know that when I multiply temperature with Boltzmann constant, I get some energy scale. So, this is some temperature, we will come to it in a minute. We define this to be equal to, we connect it to the Debye radius h bar v Kd, or we can write it as h bar omega d, where omega d is the angular frequency which is equal to v times Kd. Okay. So, in this, what are you familiar with? You are familiar only with the middle term. In the middle term, you know that V is the proportionality constant for the Debye branch, Kd is the radius of the Debye sphere, but you know that this is equal to this. So, this omega d is known as the Debye frequency. Once you know the Debye radius, you can calculate the Debye frequency. So, this is Debye frequency, and Debye frequency of what? Oscillations. And you know Kd is the upper limit of K. Therefore, omega d is the upper limit of omegas. That means this is the cutoff frequency. Above this, there are no vibrations, right, in the Debye model. So, this is the cutoff frequency. So, the Debye frequency, which is also known as the cutoff frequency. And what is theta d then? In the same spirit, theta d is called the Debye temperature, right. So, what is the interpretation of the Debye temperature? Debye temperature corresponds to the cutoff frequency, or it corresponds to the cutoff wave number, right, or it corresponds, or it represents the temperature above which the modes are not excited, isn't it? Isn't it so? Yeah. So, now we are almost done with the Debye model, just 2 more minutes. This is the main point actually. I mean I have actually done everything, and now it's just a matter of doing a little more calculation, and I don't even have to do that calculation actually. Why do I not need to do the calculation? The reason is that you know that very close to the zone boundaries, the dispersion is always linear, right? And for that, under that approximation, we have already shown that this expression gives you T cube, right? So in Debye's case, why wouldn't it give T cube? It will give T cube because we are already taking it to be linear. More important question to ask is it giving you a constant at high temperatures, right? And that also can be verified. You will get it to be equal to constant because you have maintained the number of modes. You have not exceeded the number of modes that were there in the original problem. So the high temperature and the low temperature both gets automatically fixed the way these three conditions are written here. The first condition takes care of the low temperature T cube dependence, and this condition takes care of the high temperature constant dependence. And then in the intermediate temperature range, because the actual dispersion and the Debye's dispersion are sometimes above and sometimes below, so therefore the computed specific heat for the intermediate temperatures is also, so to speak, approximately close to the experimental values, right? So just one more minute just to complete it formally. So you can then write the expression for heat capacity now, starting from here, turning it into an integration and going further and replacing omega by the Vk and setting the integration limit from 0 to Kd. That's it. So if you do that, what you're going to get is the expression for heat capacity would look something like this. So there will be C is equal to C is equal to 3. I'm writing an I'm not writing something which is the final step of calculation. So I have calculated it. I can send it to you. I'm writing something which is intermediate. So that is why you will see that it is not very nicely arranged. So we are now integrating from 0 to Kd. This is clear, right? And we are integrating over a sphere. So we'll replace d tau k, the volume element in k space, by 4 pi k square dk, right? Because now the space is isotropic. No matter which direction you go, the dispersion is always omega equals Vk, right? And this 3 is coming because you have the 3 branches and so on. So what it's going to look like is something like this: h bar Vk over, this is after taking the temperature derivative, because you have two things. You have sum over k and you have also, so sum over k is converted into integration, but you have del del t. So you can take del del t inside and differentiate the terms that are a function of temperature, right? And then you will remain with only the integration over the k variables that are a function of k. Yeah, so now in fact you don't even have two terms. There were two because you had two branches. Now you are dealing with a general case. So it will just be omega k s, and then you have h bar is already out, and n k s, and then you transform this into an integration. So this is k and s, and then moment you put omega equals Vk, so you put here Vk, and for this you put the value and then change the differential into integral. So you will get h bar del del t integral 0 to Kd, and then you have this term which is Vk, and then you have this term which is 1 over exponential beta h bar Vk minus 1 times 4 pi k square dk, that is for the volume element, and then for the density you put V over 8 pi cube. That is it. And then summation, for summation over S, you put a 3 here. That is it. And then if you take this inside and differentiate, because this only has the temperature dependence because of beta sitting here. So if you so this is like 1 over x, so its differential will be minus 1 by x square into the differential of this. So the differential of this will give you e to the power beta h bar vk, and then the differential of beta h bar vk. So because beta is 1 by t, so that will give you minus 1 by t square. So that is what is written over here. So in fact, this is, without simplifying, it's actually that the derivative of this which I have written here, beta h bar vk, and then you differentiate it, so you get h bar vk. Now it's the differential of this is h bar vk divided by t square, kb t square, and then you have into v over 8 pi cube, and then you have 4 pi k square dk. Okay, this is after the temperature derivative. Okay, and if you solve it further, you should simplify it further, and then you make one more change. You take beta h bar v k to be x. But do it at home because it's important. So you are putting beta h, so you're changing the variable. So here you will get x, and then you also have to take care of t. You have to write t in terms of x, right? So if you make those changes, which is just a matter of simplifying it further and writing dk in terms of dk in terms of dx, writing dk in terms of dx, and writing t in terms of x, so that you have only one variable, which is x. So if you do so, the final form will look like this. C is equal to 9. So this is not only C, but it is little c, and little c V, not C molar, C volume. That will be 9 N. N is number of atoms per unit volume, Kb, and then you will have T over theta D. You know what is theta D? That's the Debye temperature. Cube of this, and then integral 0 to theta D by T, and then x to the power 4 e to the power x divided by e to the power x minus 1 whole square. Yes, it is actually whole square dx. That's the final expression for the specific heat of a solid at any temperature T using the Debye model, right? And now you can, so this will be a homework, this is a homework assignment. You have to now take the two cases. Case 1, which is the high T limit. So show that this expression converges to 3R in the high T limit. And the case 2 is the low T limit, where it goes to, where the specific heat goes as T cube, right? So assume you will do that. So let's Okay, it's already, we have overrun the time, but it's, I'll just give you a hint. So suppose you want to do very low t limit. Low t meaning t is very, very small compared to theta d. If t is very small compared to theta d, what will happen to this limit? So if t is 0, then this limit will become infinite, isn't it? So this limit is very large. So you're integrating from 0 to infinity, x to the power 4 e to the power x divided by e to the power x minus 1 whole square. Now because t is very small, so therefore this quantity, so beta will be very large, right? So therefore x is a very large quantity, and therefore e to the power x is a very large quantity. So you throw away minus 1. So what you are left with is just e to the power 2x, and e to the power 2x you take it to the numerator, so it will become e to the power minus x, right, minus 2x and plus. So finally you will get an this whole thing will become a standard integral, which is 0 to infinity x to the power 4 e to the power minus x dx, and this is a standard integral using you may have seen it in maths, maybe gamma function or something, and this is a standard number. So if you do that, if you put that number, so you'll get that, you will see that the CV, little c, CV tends to 12 pi to the power 4 divided by 5 n kb t by theta d whole cube, which was already sitting here. But you don't have to say wow, because t cube तो आना ही था. जब आपने linear ले ही लिया dispersion को, t cube तो आना ही था, because already हम ये prove कर चुके हैं, right? This we have done already. But now go back to 1912 when Debye did it, and he said that look, the specific heat at low temperature goes as T cube. Okay. So similarly for high temperatures, I will not go into that. If you want, I can send you the notes.